Okay, so our first topic for today is literally straight up a review of things that were covered in Engineering 221. So we are going to be talking about instantaneous power and average power today. This is going to be a truncated explanation in as much as this is not supposed to be new material for you. Okay. So let's consider that we have a sinusoidal excitation source. Let's just call it Vs of t, acting on a linear black box network. Such that a measured voltage drop V of t is measured across the terminals of the linear black box network, and a current I of t is measured flowing into the black box network, where, due to sinusoidal excitation, V of t is of the form Vm cosine omega t plus theta v volts, and I of t is of the form Im cosine omega t plus theta I. The instantaneous power being absorbed by this linear black box network is simply P as a function of time is the product of the voltage waveform V of t and the current waveform I of t. Or Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I. Now, when we multiply these two waveforms together, we are going to be taking the product of two cosine functions. In order to make the math a little easier here, I am going to introduce a trig identity that will allow us to do this. So the trig identity that we're going to use this guy a lot over the next couple of days, is A cosine angle 1 times B cosine angle 2 looks like 1/2 AB multiplied by cosine angle 1 minus angle 2 plus cosine angle 1 plus angle 2. So if we apply that trig identity, what we will get is 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I are generic form for the instantaneous power absorbed by really any linear circuit component that we could think of, right? We have derived it here to apply to a network that could contain independent sources, dependent sources, resistors, capacitors, and inductors, and any combination thereof. This is a generic expression that will work for, again, any linear network, as long as we are able to determine the time domain voltage drop across the network and the time domain current flowing into the network. That does not mean that in order to determine the instantaneous power absorbed by such a network, we need to analyze that network in the time domain. So what I mean by that very explicitly is this voltage signal V of t contains a magnitude Vm and a phase angle theta v that is the exact same Vm and theta v that would appear in the frequency domain representation of that voltage signal. And similarly, our current waveform has a magnitude Im and a phase angle theta I that is the same as what the frequency domain representation of that current would give us. So we can literally analyze our circuit in the frequency domain and then just plug in magnitudes and phase angles as are needed to get the time domain power relationship. It is entirely unnecessary to do the analysis in the time domain. Okay, so now that I've clarified that point, I'd like to talk for a little bit about this equation. Vm is a constant value. Im is a constant value. Theta v is a constant value, and theta I is a constant value. So this first term in our equation, 1/2 Vm Im cosine theta v minus theta I, represents a constant. It has no time dependence whatsoever. So that's actually a DC contribution to our instantaneous power. So we have a DC part right here. And then the right-hand term, since it does depend on time because of that omega t dependency there, is an AC portion or an AC signal that's superimposed on top of that DC offset. So graphically, what that might look like would be something like this. And I'm just arbitrarily going to give the power a phase angle of 0 degrees to make it easier for me to draw. But we could shift it to the right or to the left as is necessary. And actually, let's scooch this down. So here's time. Here's P of t measured in watts. Time in this case will be measured in seconds. And I'm going to say that our network is absorbing a positive amount of DC power. So I'm going to put that to be something like this. And then I'm going to superimpose that AC signal in green on top of this DC value. Trying to draw it as best I can, so please bear with me. So what we should have is a sinusoidal signal that is symmetric about that DC power level, meaning exactly half of the time it's above the DC power level and exactly half of the time it's below the DC power level. And it is oscillating at twice the frequency of our voltage and current signals, okay? So what does that tell us about that DC offset? If we have a sinusoidal signal and exactly half the time it's above it and exactly half the time it's below it. Exactly right. The DC offset here represents the average power absorbed by this network. 100% correct. So we're going to call this P average. And then our instantaneous power, again represented in green, is the power that oscillates about this average point. Okay. Now in Engineering 221, we derive that relationship mathematically. I'm not going to bore you with that again. A, because it's a review, or this is supposed to be a review, and B, because this graphical representation literally does just as good a job as the math does. Okay? The DC portion has to represent the average value of this whole signal. All right, so the next thing that we are going to do is we are going to take this general equation and see what happens in the specific instances of taking the instantaneous power across a resistor and inductor, or excuse me, an inductor and a capacitor, okay? And we are going to have to use some of the relationships that we developed, particularly regarding phase angles, when we introduced our frequency domain or phasor relationships for resistors, capacitors, and inductors. So for a resistor, we know that the magnitude of the voltage drop across the resistor, Vm, is going to be Im times the resistor value. And we know that the phase angle of the voltage and the phase angle of the current have to be the same value. So if we use these relationships and plug it into our generic equation, we can write an equation for the instantaneous power absorbed by a resistor purely in terms of the voltage signal or purely in terms of the current signal, meaning that we don't have to know both pieces of information in order to calculate instantaneous and average power. Okay. So for a resistor, we can say that PR of T is still going to be 1/2 Vm times Im, right? But with a little bit of algebraic manipulation, we can see that Im is simply Vm over R. So if we express Im as Vm over R, that's going to give us 1/2 Vm squared divided by the resistor value. Now we're looking at this portion right here, cosine theta V minus theta I. Well, since theta V and theta I are equal, what's the cosine of 0? It's just 1. So we're going to have a factor of 1 plus, and now we're at this part over here, right? So cosine twice omega t, there's nothing that we can do about that. But since theta V and theta I are equal, we could just call theta V plus theta I twice theta V. And we have now represented the average power, excuse me, the instantaneous power absorbed by a purely resistive element only in terms of the voltage drop over that element. Using the opposite relationships, we can express everything only in terms of the current, which would give us 1/2 Im squared times R times a factor of 1 plus cosine twice omega t plus twice theta I. Based on these expressions, what is the average power absorbed by the resistor going to look like? It's got to be the DC portion of these expressions, which is just this times 1, or this times 1. So we could say that capital P R average must be 1/2 Vm squared over R, or alternatively 1/2 Im squared times R. And just to be very explicit that these are two different relationships, I'm going to put that bar in between. So we've used our understanding of the complex relationship between voltage and current for a resistor to express the instantaneous power absorbed by a resistor only as a function of the resistor voltage or resistor current. And then we've used these relationships to develop an average power relationship, since we know that the average power is simply the DC portion of the instantaneous power. Okay. We are going to follow this line of thought for capacitors and inductors now, starting with inductors. So for an inductor, we know that Vm is equal to omega L times Im, and we know that theta V is equal to theta I plus 90 degrees. Those relationships, again, came from our discussion of the phasor or frequency domain relationships between voltage and current for our standard passive elements that we did just before the Easter break. Okay. So for an inductor, our average power, instantaneous power, PL of t, is going to be 1/2 Vm times Im. Well, we can say that Im is Vm over omega L. And so Vm times Vm over omega L simply becomes Vm squared over omega L. Let me scroll up here real quick. So now we need to figure out what's going on with this cosine theta V minus theta I. Okay. We know that theta I could be written as theta V minus 90 degrees. We simply move this 90 degrees over to the left-hand side of this equal sign. And so theta V minus theta I would look like theta V minus the quantity theta v minus 90 degrees, which is theta v minus theta v plus 90 degrees. So what's the cosine of positive 90 degrees? It's 0. So that means that for an inductor, there will not be an average power portion because the DC offset of that signal is 0, okay? So we will simply have 1/2 Vm squared omega L times the cosine of twice omega t plus twice theta v minus 90 degrees. And now we've represented the instantaneous power absorbed by an inductor purely in terms of the voltage across the inductor. Similarly, we could say that the instantaneous power absorbed by an inductor is 1/2 Im squared omega L times the cosine of twice omega t plus twice theta I plus 90 degrees. From this, the average power absorbed by an inductor is 0. I'm only going to write it once because we could get the same result from either of these expressions. Everybody feel okay about that? So finally, we're going to look at what happens for a capacitor. So for a capacitor, we know that the magnitude of the voltage Vm is Im divided by omega c. And we know that theta I is equal to theta v plus 90 degrees from our previous discussion. So from this, the instantaneous power absorbed by our capacitor is going to be 1/2 Vm squared times omega c theta v minus theta I is going to be theta v minus theta v minus 90 degrees. What's the cosine of negative 90 degrees? 0. So again, we have no DC part. And we'll have cosine twice omega t plus twice theta v plus 90 degrees. So that's our instantaneous power only in terms of our voltage. In terms of our current, it's going to look like 1/2 Im squared over omega c cosine twice omega t plus twice theta I minus 90 degrees. And PC average is again so we have derived a generic expression for the instantaneous power absorbed by any linear network or circuit element. And then we have adapted that expression explicitly to apply to resistors, inductors, and capacitors, such that we only need to know either the voltage drop across the element or the current flowing through the element to just make our analysis a little bit easier, right? So for any element other than a resistor by itself, capacitor by itself, or inductor by itself, we have to rely on that generic expression that we first derived. These last set of equations that we've developed are only for resistors specifically, inductors specifically, and capacitors specifically. I know I mentioned this at the beginning of the class, but I'm just going to repeat it again. All of these equations effectively use our frequency domain properties. So magnitudes of voltages and currents and phase angles of voltages and currents. And we can take those quantities and apply them directly into these equations in order to get the time domain result, okay? We do not need to do any analysis in the time domain in order to utilize these. Okay, so how did you all feel about this review portion? Anything seem wild or wacky or anything like that? All right, so the next topic that I would like to talk about is the concept of maximum average power transfer. And this is new. All right, so in our discussion in Engineering 221 regarding DC circuit analysis techniques, we learned that if we could represent a two-terminal DC network by its Thevenin equivalent circuit containing a voltage source V Thevenin in series with a resistance R Thevenin, and apply that Thevenin equivalent circuit to an arbitrary load resistance RL, we could determine the voltage drop over the load resistance VL as V Thevenin times a factor of RL over R Thevenin plus RL using voltage division. We could find the current flowing through the load resistance IL using Ohm's law. So that would be simply V Thevenin divided by R Thevenin plus RL. And from these two relationships, the power, DC power, absorbed by that load resistance PL is simply the product of VL and IL, which is going to look like V Thevenin squared times RL over the quantity R Thevenin plus RL squared. Now, in circuits 1, we took this expression and we maximized. And so what I mean by that is This is fairly obviously a quadratic equation in terms of the quantity RL. So there will be a distinct value or values of RL that will give us when maximum power transfer occurs. Okay, we could literally take the derivative of this expression with respect to RL and set it equal to 0 and find whenever the maximum power, or excuse me, find what power gives us our maximum value. And in circuits 1, we discovered that maximum power transfer occurs when RL is exactly equal to R Thevenin. So that's when our original network of interest will provide the maximum amount of power to an arbitrary load resistance, is when that load resistance has the same resistance as the Thevenin resistance, okay? And we found, so when RL is equal R Thevenin, P max is simply 1/4 of V Thevenin squared divided by R Thevenin. This was our DC analysis. What we are going to introduce here is a steady state sinusoidal analog, where we are going to determine under what conditions maximum average power transfer occurs. So if we had a steady state sinusoidal circuit that we could represent by its Thevenin equivalent, meaning that we would have some phasor voltage V Thevenin in series with some impedance Z Thevenin, our goal here is to determine what load impedance ZL causes the maximum transfer of average power. And we're going to approach this in a very similar way as to what we did back in circuits 1, under the caveat now that we're going to be dealing with impedances as opposed to just resistances. Okay. So this is going to be my phasor voltage VL. This is going to be my phasor current IL. And based on our discussion a little while ago, the average power absorbed by this impedance ZL should be given by 1/2 times the magnitude of the voltage. So that would be the magnitude of VL times the magnitude of the current. So that would be the magnitude of IL times the cosine of the phase angle of the voltage, theta VL, minus the phase angle of the current, theta I. So this is literally just taking our average power relationship that we developed earlier, 1/2 Vm Im cosine theta V minus theta I, and applying that equation to the constraints of this circuit, where our voltage is VL, phasor voltage VL, and our current here is phasor current IL. Okay. So we can determine VL by using voltage division. much like we did up here in the DC case. So we could say that VL as a phasor voltage using voltage division is V Thevenin times ZL over Z Thevenin plus VL. What I'm going to do now is I'm going to break these impedances down into their constituent parts of resistance and reactance. So we're going to look at these impedances from a rectangular form complex number point of view. Okay. So that would look like phasor voltage V Thevenin times RL plus JXL divided by R Thevenin, plus JX Thevenin plus RL plus JXL. And now what I'm going to do is I'm simply going to lump together the real parts of the impedance and the imaginary parts of the impedance, giving me phasor Thevenin voltage times RL plus JXL divided by R Thev plus RL plus J X Thev plus XL. Are we all okay with that? All right. So I don't need the phasor voltage VL. I need the magnitude of this voltage. Well, this is simply a complex number. And at this point in our electrical engineering careers, we know how to take the magnitudes of complex numbers. So by inspection, the magnitude of phasor voltage VL is going to be the magnitude of V Thevenin times the square root of RL squared plus XL squared divided by the square root of R Thevenin plus RL quantity squared plus X Thevenin plus XL quantity squared. Should make sense because the magnitude of the complex number should just be the square root of the real part squared plus the imaginary part squared. We're literally just applying that to all of the rectangular portion. And I'm missing a bar up here, Miles. All right, so I'm going to put a check mark above the magnitude of VL because we figured out what that is in terms of our circuit elements. So the next thing we're going to do is try to figure out IL in a similar fashion, or the magnitude of IL explicitly. So much as we did in the DC circuit, we can simply use Ohm's law to determine IL, right? So that's going to be V Thevenin, our phasor voltage, divided by Z Thevenin plus ZL. If I break my impedances down into the rectangular form, this is going to give me V Thevenin over R Thevenin plus J X Thevenin plus RL plus JXL. And finally, just like I did previously, I'm going to lump together the real parts of my impedance and the imaginary parts of my impedance, giving me V Thevenin divided by R Thevenin plus RL plus J X Thevenin plus XL. Now I'm going to take the magnitude of this. And by inspection, we can see that this should be the magnitude of the Thevenin voltage divided by the square root of R Thevenin plus RL quantity squared plus X Thevenin plus XL quantity squared. And let's see what chat has to say. What does X represent? Bradley, X represents the reactance of our impedance, or the imaginary part of our impedance. So if you look at the end of our lecture for April the 13th, which I believe was the one we had right before Easter when we were talking about impedances, we could have a polar form representation of impedance where we simply had a magnitude and a phase angle, or a rectangular form representation of the impedance where we split it up into its constituent resistance R and reactance X. Reactances arise whenever we have capacitances and inductances. So we are just looking at a general purpose case here where we don't really care if it's a capacitance or an inductance, just that there's a possibility of it having some overall capacitance or some overall inductance that we need to account for. All right, so that is exactly what it is. I'm going to put a check mark by the magnitude of IL because we've got that down as well. So now we need to come up with a relationship for cosine theta VL minus theta IL. And this is probably less intuitive. If the other parts were intuitive at all, this is less so. How I'm going to come up with this relationship is I'm going to look at the impedance ZL on the complex plane. Okay. So I have a complex plane like such, where the positive x-axis is used for real numbers and the positive y-axis is used for imaginary numbers. The rectangular form of my impedance RL is just going to be effectively a vector in this 2D coordinate system, right? It's going to have some length in the real direction, and it's going to have, which is given by its resistance, and it's going to have some length in the imaginary direction, which is given by its reactance. I am going to arbitrarily assume here that both of those are positive quantities, but it really is not important in any way, shape, or form, okay? So let's say that this vector represents ZL. Okay. This angle right here theta ZL is simply theta VL minus theta IR from the literal definition of impedance. So we want the cosine of that angle. From our high school trig classes, the cosine of the angle is what? The adjacent over the hypotenuse, right? Is that correct, or is it the opposite? I think it's the adjacent. Okay. So the adjacent here simply represents the resistance RL. The opposite bit here represents the reactance XL. And so cosine theta VL minus theta IL is just RL, the adjacent, divided by the hypotenuse, which is given by simply the square root of RL squared plus XL squared using our good old Pythagorean theorem. So I now know all of the constituent parts of this equation, which tells me what my average power should be. So once I smash all these things together, then I can actually figure out how to maximize this thing in order to determine when or for what value of ZL does maximum average power transfer occur. Okay. So plugging in these results, I will find that PL average, so the average power absorbed by my load impedance ZL, is given by 1/2 times the magnitude of VL take me a minute to write all this gibberish down. So here we have the magnitude of V thev, and then the square root of RL squared plus XL squared. This big piece right here represents the magnitude of VL. Now I'm going to substitute in my representation for the magnitude of IL. So that's going to have the exact same big ugly denominator. My numerator is just going to be the magnitude of V thev. And then finally, cosine theta V minus theta I, as we found out a few moments ago, is simply RL divided by the square root of RL squared plus XL squared. Okay, so now it's time to do a couple of little simplification type things here. So the first thing that we can observe is that we have a factor of square root RL squared plus XL squared here in the numerator, and another one down here in the denominator. So those two obviously cancel each other out. Another thing that we can observe is that we're going to have the magnitude of V Thevenin times the magnitude of V Thevenin, which is just the magnitude of V Thevenin squared. And then we have this same denominator, which is the square root. So we're going to get rid of that square root sign. Okay. So this is going to look like 1/2 the magnitude of V Thevenin squared times RL divided by R Thevenin plus RL quantity squared plus X Thevenin plus XL quantity squared. So we have an expression for our average power generically. Now we need to figure out when maximum power transfer occurs. So let me ask you guys a question. What does the reactance in this expression do? Does it make exactly right? So having any reactance whatsoever causes our average power to decrease because it only appears in the denominator, right? So in order to cause maximum average power transfer to occur, we need X Thevenin and XL to cancel each other out, reducing this term to 0. So that means XL needs to equal exactly negative X Thevenin for maximum average power transfer to occur. But that's only part of it, right? Because we still have to then maximize what's happening with the resistances. So under this constraint, that XL is exactly equal to negative X Thevenin, our average power representation, so I'm going to call this PL average prime, no derivative or anything like that, just saying that it's not the full thing that we're trying to maximize. We're left with the magnitude of V Thevenin squared times RL over R Thevenin plus RL quantity squared. Well, if we neglect this factor of 1/2, this is literally the exact same expression that we maximized in 221 to determine the DC value. Okay. So by recognizing that this is the exact same expression that we maximized previously, we know this achieves its maximum value when RL is exactly equal to R Thevenin. Putting these results together, maximum average power is transferred when ZL is equal to R Thevenin minus J X Thevenin, which is simply the complex conjugate of E7. Excuse me, Z7, thank you. So intuitively, this should make sense, because if we had two impedances that were in series with each other and their imaginary parts canceled each other out, maximum power transfer should occur. And then we've got the real parts set in such a way that effectively the voltage drop over the real parts divides evenly across the two, causing maximum average power transfer. So under this constraint, where ZL is exactly equal to Z Thevenin, the maximum power absorbed by our load impedance comes out to be 1/8 the magnitude of our Thevenin voltage squared divided by, excuse me, instead of having RL here, let's put RThev. This is exactly the same as we have right here, except that we have that extra power of 1/2 because we're multiplying sinusoidal functions. All right. I believe that that is enough out of me for today, because we don't even really have enough time to get started on our next topic, which would be instantaneous power absorbed by a multi-frequency circuit, which is what we're going to kick things off with on Monday. So I am going to get a couple of homework assignments put up for you guys here this afternoon. I need to go through, typically speaking, for the steady state sinusoidal portion review. So that just the steady state sinusoidal circuit analysis review. I typically assign 2 homework assignments. I'm going to consolidate those 2 homework assignments into a single one. And I don't mean I'm just going to give you one assignment that's twice as long. I'm going to cut some problems so that it's of a reasonable length for you guys to do. And then I'm going to give an assignment over the material that was explicitly covered today. So expect 2 homework assignments to be put up here pretty shortly. The one on the steady state sinusoidal analysis will be due next Friday, and then the one over this material will be due the following Monday, so that I'm giving you enough time to actually get it done. So I'm not going to cut off time for you to work on it because I was late in putting it up.